Section 4.1, Correlation. A correlation exists between two variables when a relationship between the two variables exists. The data is called paired data because you measure two different things from the same person. For example, a person's height or shoe size. Okay, it doesn't have to be people, it can be other things too. A positive relationship means that as one variable increases, the other increases also. They both get bigger. For example, how much electricity I use and my bill. As the amount of usage increases, so does my bill. Miles run and calories burned. As the number of miles run increases, so does the number of calories. A negative relationship means that as one variable increases, the other decreases. One goes up and one goes down. Car payments made and balance left. As the number of car payments made increase, the balance left decreases. The weight of a vehicle and fuel efficiency. As the weight of a vehicle increases, the fuel efficiency decreases. That means how many miles per gallon you get. Bigger cars get worse gas mileage. No correlation means that a pattern does not exist. The two variables are not related. Example, height and IQ. Height has no effect on someone's IQ. Shoe size and the number of children someone has. There's no relationship, no connection. A linear correlation coefficient is a method to calculate the relationship of correlation. The values must be between -1 and +1. Okay. A correlation coefficient of -1 means a perfect negative correlation. Okay. That means it goes exactly down. There's no outliers. There's no things that aren't in place. A correlation coefficient of 0 means no correlation. A correlation coefficient of 1 means a perfect positive correlation. They go up exactly the same every time. The closer the coefficient gets to -1, the stronger the negative correlation. The closer it gets to +1, the stronger positive correlation. Numbers that are close to 0 indicate there's no relationship. Think about a number line. Okay, so if you're at 0, there's no correlation. Things like 0.1, -0.1, 0.2, or -0.2 are probably no relationship. Okay, but as we get closer to 0.7, 0.8, 0.9, we're getting a much stronger correlation. -7, -8, -0.7, -0.8, -0.9. Okay, as you get closer to -1, you're getting a stronger negative correlation. Okay, that means there's not really any exceptions to the rule. Okay, comparing correlation. Example 1. -0.95 and -0.75. Those would both be negative correlation. -0.95 would be a stronger one since 0.95 is closer to 1. So -0.95 is closer to -1. 0.75 and 0.95 would both be positive. 0.95 would be stronger since it's closer to 1. Numbers close to 0 are not correlated. 0.25 or -0.34. A stronger correlation means the graph looks closer to a line. Positive correlations are a line going up from left to right. Negative correlations are a line going down from left to right. No correlation has no pattern. Okay. There could also be a pattern, but if the pattern does not look like a line, it's not a linear correlation. Linear means line. Okay. The explanatory variable is x. It's the variable that affects others. The response variable is y, and it's the variable that's affected by x. Example, as electricity usage increases, so does my bill. The explanatory variable is usage, response is bill. Usage affects the bill. Okay, so let's look at our first row of graphs. A is a perfect positive correlation because it's a perfect straight line, and that would be a correlation of 1. And the variable for the linear correlation coefficient is r. Okay, let's look at B. It's pretty close to a line, but it's not a perfect line like A. Okay, so it would probably have a correlation coefficient R pretty close to 0.9. Okay, C, that's moderate. It sort of looks like a line, but it's not as strong as B, and it's definitely not as strong as A. Okay, the dots are more spread out. So we would say maybe 0.4 for its correlation. Okay, now D, we're going down. It's a perfect straight line, so R equals -1. E, a strong negative correlation. Okay, it looks like a pretty good straight line, and it's going down, so it would be about -0.9 for R. Okay, F, the dots are not as close together, but it sort of forms a line going down, so maybe R would be -0.4, 0.5, -0.5. G, the dots are all spread out, there's no pattern, R is close to 0. Okay, now let's look at H. There is a pattern, but you see how it's a curve? It's not a line, so we would say R is close to 0. One thing about correlation, we must be careful when interpreting it. Just because they're correlated does not mean that one causes the other. We say correlation does not imply causation. There are many good examples of correlation which are nonsensical when interpreted in terms of causation. Okay? Ice cream sales and the number of shark attacks on swimmers can be shown to be correlated. Cola consumption and bone density. There's probably a common response that both things change because of something else. Ice cream sales and shark attacks both increase probably because more people buy ice cream and swim when the temperatures increase. Okay. Other factors probably affect both. It's not necessarily the colas themselves, but it could be eating habits in general. A more specific experiment would be needed to keep all the other variables the same to show that bone density is affected by drinking soda. Scatter plots plot the data. The explanatory variable is x, and it goes along this bottom axis called the x-axis. The response variable y is the one that goes up on the left. Okay, look to see if the graph looks like a line. So shoe size and IQ, we can see there's no relationship there. Okay, what about hours of exercise and resting heart rate? Okay, so we have hours along the bottom. The heart rate is in beats per minute, BPM. And it sees that as the more somebody exercises, their resting heart rate goes down. Okay, this is the resting heart rate when you're sitting still, not doing anything. Okay, and that's a good thing to have a lower resting heart rate. Okay, what about education and income? Okay, so we have a table here, education years and income in thousands. So that means this means 22,000, 63,000. So we have years of education along our X, income in thousands going up. The first person has 12 years of income, of years of education, and 22,000 income. Okay, so all of these dots represent a person. Okay, so this first dot right here, we have the 10 years of education and $14,000. So that's our 10, 14 right here. Each dot represents a person, their income, and their education. See how this mostly forms a line? This pattern right here going up. And we have two dots that are way outside here, okay? Way outside this normal pattern, all right? We have these two dots, we call these outliers. They lie outside the general pattern, okay? So one of them is the 14-2, okay? This dot right here, 14 years of education, 2,000 income, okay? This person could still be in school. They could be a stay-at-home parent. Okay, that would be the reason, some possible reasons why they're not in this pattern. Okay, we have another outlier here, and it is this 1197. Somebody with 11 years of education and $97,000, okay, of income. Just because someone does not have a college degree does not mean they will not make a lot of money. They could own their own business that's very profitable. My neighbor is a lineman, electrician, and makes more money than I do. He's just starting out, and I've got 20 years experience. Okay, so there's a general pattern here, but we always have these exceptions. And that's the end of this lesson.